Message Passing Interface is a standardized and portable message passing system designed by a group of researchers from academia and industry to function on a wide variety of parallel computers. The standard defines the syntax and semantics of a core of library routines useful to a wide range of users writing portable message passing programs in different computer programming languages such as Fortran, C, C++, and Java. There are several well-tested and efficient implementations of Mpi, including some that are free or in the public domain. These fostered the development of a parallel software industry, and encouraged development of portable and scalable large-scale parallel applications. History: the message passing interface effort began in the summer of 1991 when a small group of researchers started discussions at a mountain retreat in Austria. Out of that discussion came a workshop on standards for message passing in a distributed memory environment held on April 29, 1992 in Williamsburg, Virginia. At this workshop the basic features essential to a standard message passing interface were discussed, and a working group established to continue the standardization process. Jack Dongara, Rolf Hempel, Tony Hay, and David W. Walker put forward a preliminary draft proposal in November 1992. This was known as Mpi-1. In November 1992, a meeting of the Mpi working group was held in Minneapolis, at which it was decided to place the standardization process on a more formal footing. The Mpi working group met every 6 weeks throughout the first 9 months of 1993. The draft Mpi standard was presented at the Supercomputing 93 conference in November 1993. After a period of public comments, which resulted in some changes in Mpi, version 1.0 of Mpi was released in June 1994. These meetings and the email discussion together constituted the Mpi Forum, membership of which has been open to all members of the high-performance computing community. The Mpi effort involved about 80 people from 40 organizations, mainly in the United States and Europe. Most of the major vendors of concurrent computers were involved in Mpi along with researchers from universities, government laboratories, and industry. The Mpi standard defines the syntax and semantics of a core of library routines useful to a wide range of users writing portable message passing programs in Fortran and C. Mpi provides parallel hardware vendors with a clearly defined base set of routines that can be efficiently implemented. As a result, hardware vendors can build upon this collection of standard low-level routines to create higher-level routines for the distributed memory communication environment supplied with their parallel machines. Mpi provides a simple-to-use portable interface for the basic user, yet powerful enough to allow programmers to use the high-performance message passing operations available on advanced machines. As an effort to create a true standard for message passing, researchers incorporated the most useful features of several systems into Mpi, rather than choose one system to adopt as a standard. Features were used from systems by IBM, Intel, N-Cube, PVM, Express, P4 and Parmax. The message passing paradigm is attractive because of wide portability and can be used in communication for distributed memory and shared memory multiprocessors, networks of workstations, and a combination of these elements. The paradigm is applicable in multiple settings, independent of network speed or memory architecture. Support for Mpi meetings came in part from ARPA and U.S. National Science Foundation under Grant ASC 9310330, NSF Science and Technology Center Cooperative Agreement Number CCR 8809-615, and the Commission of the European Community through Esprit Project P6643. The University of Tennessee also made financial contributions to the Mpi Forum. Overview: Mpi is a language-independent communications protocol used to program parallel computers. Both point-to-point and collective communication are supported. Mpi is a message passing application programmer interface, together with protocol and semantic specifications for how its features must behave in any implementation. Mpi's goals are high performance, scalability, and portability. Mpi remains the dominant model used in high-performance computing today. Mpi is not sanctioned by any major standards body. Nevertheless, it has become a de facto standard for communication among processes that model a parallel program running on a distributed memory system. Actual distributed memory supercomputers such as computer clusters often run such programs. The principal Mpi-1 model has no shared memory concept, and Mpi-2 has only a limited distributed shared memory concept. Nonetheless, Mpi programs are regularly run on shared memory computers. Designing programs around the Mpi model has advantages over NUMA architectures since Mpi encourages memory locality. Although Mpi belongs in layers 5 and higher of the OSI reference model, implementations may cover most layers, with sockets and transmission control protocol used in the transport layer. Most Mpi implementations consist of a specific set of routines directly callable from C, C++, Fortran and any language able to interface with such libraries, including C, Java or Python. The advantages of Mpi over older message passing libraries are portability and speed. Mpi uses language-independent specifications for calls and language bindings. The first Mpi standard specified ANSIC and Fortran 77 bindings together with the LIS. The draft was presented at Supercomputing 1994 and finalized soon thereafter. About 128 functions constitute the Mpi 1.3 standard, which was released as the final end of the Mpi 1 series in 2008. At present, the standard has several versions: version 1.3, which emphasizes message passing and has a static runtime environment, Mpi 2.2, which includes new features such as parallel I/O, dynamic process management and remote memory operations, and Mpi 3.0, which includes extensions to the collective operations with non-blocking versions and extensions to the one-sided operations. Mpi-2's LIS specifies over 500 functions and provides language bindings for ANSIC, ANSIC++, and ANSI Fortran. Object interoperability was also added to allow easier mixed-language message passing programming. A side effect of standardizing Mpi-2, completed in 1996, was clarifying the Mpi-1 standard, creating the Mpi 1.2. Mpi-2 is mostly a superset of Mpi-1, although some functions have been deprecated. Mpi 1.3 programs still work under Mpi implementations compliant with the Mpi-2 standard. Mpi-3 includes new Fortran 2008 bindings, while it removes deprecated C++ bindings as well as many deprecated routines and Mpi objects. Mpi is often compared with Parallel Virtual Machine, which is a popular distributed environment and message passing system developed in 1989, and which was one of the systems that motivated the need for standard parallel message passing. Threaded shared memory programming models and message passing programming can be considered as complementary programming approaches, and can occasionally be seen together in applications, for example in servers with multiple large shared memory nodes. Functionality: the Mpi interface is meant to provide essential virtual topology, synchronization, and communication functionality between a set of processes in a language-independent way, with language-specific syntax, plus a few language-specific features. Mpi programs always work with processes, but programmers commonly refer to the processes as processors. Typically, for maximum performance, each CPU will be assigned just a single process. This assignment happens at runtime through the agent that starts the Mpi program, normally called Mpi or Mpi. Mpi library functions include, but are not limited to, point-to-point rendezvous type send-receive operations, choosing between a Cartesian or graph-like logical process topology, exchanging data between process pairs, combining partial results of computations, synchronizing nodes as well as obtaining network-related information such as the number of processes in the computing session, current processor identity that a process is mapped to, neighboring processes accessible in a logical topology, and so on. Point-to-point operations come in synchronous, asynchronous, buffered, and ready forms, to allow both relatively stronger and weaker semantics for the synchronization aspects of a rendezvous send. Many outstanding operations are possible in asynchronous mode, in most implementations. Mpi-1 and Mpi-2 both enable implementations that overlap communication and computation, but practice and theory differ. Mpi also specifies thread-safe interfaces, which have cohesion and coupling strategies that help avoid hidden state within the interface. It is relatively easy to write multi-threaded point-to-point Mpi code, and some implementations support such code. Multi-threaded collective communication is best accomplished with multiple copies of communicators, as described below. Concepts: Mpi provides a rich range of abilities. The following concepts help in understanding and providing context for all of those abilities and help the programmer to decide what functionality to use in their application programs. 4 of Mpi's 8 basic concepts are unique to Mpi-2. Communicator. Communicator objects connect groups of processes in the Mpi session. Each communicator gives each contained process an independent identifier and arranges its contained processes in an ordered topology. Mpi also has explicit groups, but these are mainly good for organizing and reorganizing groups of processes before another communicator is made. Mpi understands single group intra-communicator operations, and bilateral intercommunicator communication. In Mpi-1, single group operations are most prevalent. Bilateral operations mostly appear in Mpi-2 where they include collective communication and dynamic in-process management. Communicators can be partitioned using several Mpi commands. These commands include Mpi CommSplit, where each process joins one of several colored sub-communicators by declaring itself to have that color. Point-to-point basics. A number of important Mpi functions involve communication between two specific processes. A popular example is Mpi Send, which allows one specified process to send a message to a second specified process. Point-to-point operations, as these are called, are particularly useful in patterned or irregular communication, for example, a data parallel architecture in which each processor routinely swaps regions of data with specific other processors between calculation steps, or a master-slave architecture in which the master sends new task data to a slave whenever the prior task is completed. Mpi-1 specifies mechanisms for both blocking and non-blocking point-to-point communication mechanisms, as well as the so-called ready send mechanism whereby a send request can be made only when the matching receive request has already been made. Collective basics. Collective functions involve communication among all processes in a process group. A typical function is the Mpi-BCAST call. This function takes data from one node and sends it to all processes in the process group. A reverse operation is the Mpi-reduce call, which takes data from all processes in a group, performs an operation, and stores the results on one node. Reduce is often useful at the start or end of a large distributed calculation, where each processor operates on a part of the data and then combines it into a result. Other operations perform more sophisticated tasks, such as Mpi-Altol, which rearranges n items of data processor such that the nth node gets the nth item of data from each. Derived data types. Many Mpi functions require that you specify the type of data which is sent between processes. This is because these functions pass variables, not defined types. If the data type is a standard one, such as int, char, double, etc., you can use predefined Mpi data types such as Mpi-int, Mpi-char, Mpi-double. Here is an example in C that passes an array of ints and all the processes want to send their arrays to the root with Mpi-gather. However, you may instead wish to send data as one block as opposed to 100 ints. To do this, define a contiguous block-derived data type. Passing a class or a data structure cannot use a predefined data type. Mpi type create struct creates an Mpi-derived data type from Mpi predefined data types, as follows. Where count is a number of blocks, also number of entries in blocklen, disp, and type, blocklen a number of elements in each block, disp a byte displacement of each block, type a type of elements in each block. The disp array is needed because processors require the variables to be aligned a specific way on the memory. For example, char is 1 byte and can go anywhere on the memory. Short is 2 bytes, so it goes to even memory addresses. Long is 4 bytes, it goes on locations divisible by 4 and so on. The compiler tries to accommodate this architecture in a class or data structure by padding the variables. The safest way to find the distance between different variables in a data structure is by obtaining their addresses with Mpi getAddress. This function calculates the displacement of all the structure's elements from the start of the data structure. Given the following data structures. Here's the C code for building an Mpi-derived data type. Mpi-2 concepts, one-sided communication. Mpi-2 defines 3 one-sided communications operations, put, get, and accumulate, being a write to remote memory, a read from remote memory, and a reduction operation on the same memory across a number of tasks, respectively. Also defined are 3 different methods to synchronize this communication, as the specification does not guarantee that these operations have taken place until a synchronization point. These types of call can often be useful for algorithms in which synchronization would be inconvenient, or where it is desirable for tasks to be able to balance their load while other processes are operating on data. Collective extensions, this section needs to be developed. Dynamic process management, the key aspect is the ability of an Mpi process to participate in the creation of new Mpi processes or to establish communication with Mpi processes that have been started separately. The Mpi-2 specification describes 3 main interfaces by which Mpi processes can dynamically establish communications: Mpi-Com spawn, Mpi-Com accept, Mpi-Com connect, and Mpi-Com join. The Mpi-Com spawn interface allows an Mpi process to spawn a number of instances of the named Mpi process. The newly spawned set of Mpi processes form a new Mpi-Com world intra-communicator but can communicate with the parent and the intercommunicator the function returns. Mpi-Com spawn multiple is an alternate interface that allows the different instances spawned to be different binaries with different arguments. I/O, the parallel I/O feature is sometimes called Mpi I/O, and refers to a set of functions designed to abstract I/O management on distributed systems to Mpi, and allow files to be easily accessed in a patterned way using the existing derived data type functionality. The little research that has been done on this feature indicates the difficulty for good performance. For example, some implementations of sparse matrix vector multiplications using the Mpi I/O library are disastrously inefficient. Implementations, classical cluster and supercomputer implementations. The Mpi implementation language is not constrained to match the language or languages it seeks to support at runtime. Most implementations combine C, C++, and assembly language, and target C, C++, and Fortran programmers. Bindings are available for many other languages, including Perl, Python, R, Ruby, Java, CL. The initial implementation of the Mpi-1x standard was Mpi-CH, from Argonne National Laboratory and Mississippi State University. IBM also was an early implementer, and most early 90s supercomputer companies either commercialized Mpi-CH, or built their own implementation. LAM Mpi from Ohio Supercomputer Center was another early open implementation. ANL has continued developing Mpi-CH for over a decade, and now offers Mpi-CH2, implementing the Mpi 2.1 standard. LAM Mpi and a number of other Mpi efforts recently merged to form Open Mpi. Many other efforts are derivatives of Mpi-CH, LAM, and other works, including, but not limited to, commercial implementations from HP, Intel, and Microsoft. Python, Mpi Python implementations include, PyMpi, Mpi-4py, Piper, MyMpi, and the Mpi submodule and Scientific Python. PyMpi is notable because it is a variant Python interpreter, while Piper, MyMpi, and Scientific Python's module are import modules. They make it the coder's job to decide where the call to Mpi init belongs. Recently the well-known Boost C++ libraries acquired Boost, Mpi, which included the Mpi Python bindings. This is of particular help for mixing C++ and Python. OCaml, The OCaml Mpi module implements a large subset of Mpi functions and is in active use in scientific computing. An 11,000-line OCaml program was Mpi-ified using the module, with an additional 500 lines of code and slight restructuring, and ran with excellent results on up to 170 nodes in a supercomputer. Java. Although Java does not have an official Mpi binding, several groups attempt to bridge the two, with different degrees of success and compatibility. One of the first attempts was Brian Carpenter's Mpi Java, essentially a set of Java native interface wrappers to a local Mpi library, resulting in a hybrid implementation with limited portability, which also has to be compiled against the specific Mpi library being used. However, this original project also defined the Mpi Java API, which other subsequent Java Mpi projects adopted. An alternative, less used API is Mpj API, designed to be more object-oriented and closer to Sun Microsystems coding conventions. Beyond the API, Java Mpi libraries can be either dependent on a local Mpi library, or implement the message passing functions in Java, while some like P2P Mpi also provide peer-to-peer functionality and allow mixed platform operation. Some of the most challenging parts of Java Mpi arise from Java characteristics such as the lack of explicit pointers and the linear memory address space for its objects, which make transferring multidimensional arrays and complex objects inefficient. Workarounds usually involve transferring one line at a time and/or performing explicit deserialization and casting at both sending and receiving ends, simulating C or Fortran-like arrays by the use of a one-dimensional array, and pointers to primitive types by the use of single-element arrays, thus resulting in programming styles quite far from Java conventions. Another Java message passing system is Mpj Express. Recent versions can be executed in cluster and multi-core configurations. In the cluster configuration, it can execute parallel Java applications on clusters and clouds. Here Java sockets or specialized I/O interconnects like MyRinit can support messaging between Mpj Express processes. It can also utilize native C implementation of Mpi using its native device. In the multi-core configuration, a parallel Java application is executed on multi-core processors. In this mode, Mpj Express processes are represented by Java threads. Matlab. There are a few academic implementations of Mpi using Matlab. Matlab has their own parallel extension library implemented using Mpi and PVM. Our implementations of Mpi include our Mpi and PBD-Mpi, where our Mpi focuses on manager workers parallelism while PBD-Mpi focuses on SPMD parallelism. Both implementations fully support OpenMPI or Mpi-ch2. Common Language Infrastructure. The two managed Common Language Infrastructure.NET implementations are PureMPI.NET and Mpi.NET, a research effort at Indiana University licensed under a BSD-style license. It is compatible with Mono, and can make full use of underlying low-latency Mpi network fabrics. Hardware implementations. Mpi hardware research focuses on implementing Mpi directly in hardware, for example via processor in memory, building Mpi operations into the microcircuitry of the RAM chips in each node. By implication, this approach is independent of the language, OS or CPU, but cannot be readily updated or removed. Another approach has been to add hardware acceleration to one or more parts of the operation, including hardware processing of Mpi queues and using RDMA to directly transfer data between memory and the network interface without CPU or OS kernel intervention. Mpi is a program which helps the programmer to use a standard C programming language, compile it together with the message passing interface libraries, most commonly the OpenMPI implementation which is found in many TOP 500 supercomputers, for the purpose of producing parallel processing programs to run over computer clusters. The Mpi program uses a programmer's preferred C compiler and takes care of linking it with the Mpi libraries. Example program. Here is a Hello World program in Mpi written in C. In this example, we send a hello message to each processor, manipulate it trivially, return the results to the main process, and print the messages. When run with two processors, this gives the following output. 0. We have two processors, 0, hello 1. Processor 1 reporting for duty. The runtime environment for the MPI implementation used spawns multiple copies of the program, with the total number of copies determining the number of process ranks in Mpi Comm world, which is an opaque descriptor for communication between the set of processes. A single process, multiple data programming model is thereby facilitated, but not required. Many MPI implementations allow multiple, different, executables to be started in the same MPI job. Each process has its own rank, the total number of processes in the world, and the ability to communicate between them either with point-to-point communication, or by collective communication among the group. It is enough for MPI to provide an SPMD-style program with Mpi Comm world, its own rank, and the size of the world to allow algorithms to decide what to do. In more realistic situations, I/O is more carefully managed than in this example. Mpi does not guarantee how POSIX I/O would actually work on a given system, but it commonly does work, at least from rank 0. Mpi uses the notion of process rather than processor. Program copies are mapped to processes by the Mpi runtime. In that sense, the parallel machine can map to one physical processor, or n, where n is the total number of processors available, or something in between. For maximum parallel speed-up, more physical processors are used. This example adjusts its behavior to the size of the world n, so it also seeks to scale to the runtime configuration without compilation for each size variation, although runtime decisions might vary depending on that absolute amount of concurrency available. Mpi-2 adoption. Adoption of Mpi 1.2 has been universal, particularly in cluster computing, but acceptance of Mpi 2.1 has been more limited. Issues include, Mpi-2 implementations include I/O and dynamic process management, and the size of the middleware is substantially larger. Most sites that use batch scheduling systems cannot support dynamic process management. Mpi-2's parallel I/O is well accepted. Many Mpi 1.2 programs were developed before Mpi-2. Portability concerns initially slowed, although wider support has lessened this. Many Mpi 1.2 applications use only a subset of that standard with no real need for Mpi-2 functionality. Future. Some aspects of Mpi's future appear solid. Others less so. The Mpi Forum reconvened in 2007, to clarify some Mpi-2 issues and explore developments for a possible Mpi-3. Like Fortran, Mpi is ubiquitous in technical computing, and it is taught and used widely. Architectures are changing, with greater internal concurrency, better fine-grained concurrency control, and more levels of memory hierarchy. Multi-threaded programs can take advantage of these developments more easily than single-threaded applications. This has already yielded separate, complementary standards for symmetric multiprocessing, namely OpenMP. Mpi-2 defines how standard-conforming implementations should deal with multi-threaded issues, but does not require that implementations be multi-threaded, or even thread-safe. Few multi-threaded capable Mpi implementations exist. Multi-level concurrency completely within Mpi is an opportunity for the standard. See also. References. Further reading. External links, Mpi examples, Message Passing Interface. Haken Habida, University of Houston. Retrieved October 2012. A Message Passing Interface at DMOZ, Tutorial on Mpi, the Message Passing Interface A User's Guide to Mpi.